Welcome to Part B of Unit 2 for our course on statistics. And we've been talking about different ways of assessing effect size. In our previous section, we were looking at a D statistic and looking at how we can use a D statistic to measure an effect size, and how a D statistic was especially appropriate when you have one dichotomous variable and one numerically scaled variable. That is, you're looking at a difference between two groups in some numerically scaled outcome. A correlation is another way of measuring an effect size, and a correlation is going to be especially appropriate when you have two numerically scaled variables. So this would be a situation where you don't have any group variables, you don't have any categorical variables, all your variables are numerically scaled. They're all variables that range from high to low. Now, as we'll be seeing later on, we actually can use a correlation in situations where I have categorical variables. It's just that a correlation isn't as easy to interpret in those situations. So a correlation is especially easy to interpret when we have two numerically scaled variables, two variables that range from high to low. And that's what we'll be focusing on here. And the correlation is going to give us an effect size, or it'll give us the strength of relationship between these two numerically scaled variables. And you may already be familiar with a correlation and know that a correlation tells us about the strength of relationship between two numerically scaled variables on a scale that ranges from -1, which means a perfect negative relationship, to 0, which means absolutely no relationship, to 1, which means perfect positive relationship. So, for example, say I was doing a study on, well, maybe I had a sample of people that had all had a recent accident where they dropped a rock on their foot. So I have a sample of people that recently dropped a rock on their foot, and say I did a study where I measured the size of the rock that they dropped on their foot, and I measured the amount of pain that they felt after they dropped the rock on their foot. And so the size of the rock would be one numerically scaled variable. It would range from high to low. And the amount of pain they felt would be another numerically scaled variable. It would range from high to low. And I would probably find that there was a positive relationship between those two variables, meaning as the size of the rock went up, the amount of pain went up. As the size of the rock went down, the amount of pain went down. So a positive relationship means as one variable goes up, the other goes up. As one variable goes down, the other goes down. Now, if they went up and down in perfect unison, that would be a perfect positive relationship, a correlation of 1. If there was a perfect positive relationship, that would mean if I knew the size of the rock, I could perfectly predict their pain. If I knew the amount of pain, I could perfectly predict the size of the rock, because those two variables go up and down in unison together the exact same amount each. So if I knew your score on one, I could know exactly what your score is on the other. And that would be a perfect positive relationship. Now, if I did my study where I looked at, say, the size of the rock and had people rate the happiness that they felt after they dropped the rock on their foot, I might find that there's a negative relationship between the size of the rock and the amount of happiness people experience. In this case, as one variable goes up, the other one goes down, and vice versa. Or if I did a study where I looked at, say, the amount of pain that people felt after they dropped the rock on their foot, and maybe the age at which they were first potty trained, that their age of potty training, I might find there's no relationship whatsoever between the age at which someone was potty trained and the amount of pain they felt when a rock was dropped on their foot. Those would both be numerically scaled variables. Age of potty training goes up and down. That can range from high to low, and the amount of pain can range from high to low. But in this case, I would guess there's probably no relationship whatsoever, that the potty training experiences probably have nothing to do with the amount of pain people experience when they drop rocks on their foot. Now, let's take a closer look at a correlation so you can understand exactly what it is and how to calculate it. And the first step to understanding a correlation and to being able to calculate a correlation is to understand something called a covariance. And once we explain what a covariance is, it's very easy to explain what a correlation is. So what is a covariance? Well, the easiest way to explain what a covariance is to compare a covariance with a variance. And we've already talked about a variance. So a variance is where we take the sum of squares for a variable and divide by our degrees of freedom, and that will give us our variance. Or if we wanted to, we could take the square root of our variance, and that would give us our standard deviation. We're not going to deal with standard deviations right here, but if we wanted to, we could take the square root of our variance and get a standard deviation. So, for example, in my study where I had people who had all had a recent accident where they dropped a rock on their foot, one variable in that study might be rock size, the size of the rock that was dropped on each person's foot. And so rock size would be a numerically scaled variable. It would range from high to low. And so if we calculated the variance for rock size, if rock size was variable x, we could calculate the variance for rock size where we take each person's score on x, the rock size for each person, minus the average rock size that was dropped on people's feet. So x minus x bar, and then we square that deviation to get a square deviation. Then we sum that up for all the people in our sample to get the sum of squares, divide by n minus 1, and we get our variance. Now, I have this on the top here, I have the regular way we write the formula for the variance. Right underneath, I've written this formula out the long way. It's an alternate way of writing the exact same formula. And instead of saying x minus x bar squared, I say x minus x bar times x minus x bar. So it's the exact same thing. I've just written it out the long way. Rather than saying x minus x bar squared, I say x minus x bar times x minus x bar. Now, note that what we're doing here in the formula is we have a centered score. We have your centered score on rock size, your centered score on x, and we're multiplying that centered score on x by itself. So we have your score on centered x score times itself, sum that up for everyone in the sample to divide by degrees of freedom, and you have your variance. Now let's compare our formula for a variance, the bottom one here. It makes it easy to compare with a covariance. Let's look at how that compares with the covariance formula on the right. And you'll note these two formulas are almost identical with one slight change, and it's simply right here on the right hand side of our numerator is our variable an x or a y. So with a variance, it's centered x times itself, centered x times centered x. With a covariance, it's centered x times centered y. It's x minus x bar times y minus y bar. So a variance is a formula we can compute when I have just a single variable. A covariance is a formula I can compute when I have a pair of variables, two variables, a variable x and a variable y. So maybe variable x is the size of the rock that was dropped on someone's foot, and variable y is the amount of pain they felt after the rock was dropped on their foot. So I have rock size and pain, two separate variables. So I have each person's score on x, I have each person's score on y, and I center everyone's score on x, x minus x bar. I center everyone's score on y, y minus y bar, and with a covariance, I take centered x times centered y. And I do that for every single person in my sample, sum that up to get, in this case, I'll call this a sum of cross products. So with a variance, I calculate something called the sum of squares, a variable times itself, centered x times itself. With a covariance, I calculate something called the sum of cross products, the sum of centered x times centered y. And then in both cases, I divide by my degrees of freedom. So in some ways, we can think of the variance as kind of a, well, maybe kind of a narcissistic. It's like me and me. It's like me looking at myself in a mirror. It's like centered x times itself. It's me and me, centered x times myself. Whereas a covariance is more of a social, friendly type of thing. It's me and a partner, x and y together. It's centered x times centered y. So the key difference between a variance and a covariance is simply, are we talking about centered x times itself or centered x times centered y? Otherwise, in both cases, we add up those scores, the sum of squares or the sum of products, sum of cross products, and then we divide by degrees of freedom. And if it's the sum of squares divided by degrees of freedom, we have a variance. If it's a sum of cross products divided by degrees of freedom, it's a covariance. So that's what a covariance is. But at this point, you might be wondering, okay, well, that's a nifty formula, but what good is it for? Why would I want to calculate a covariance? Well, as it turns out, a covariance just by itself, with nothing else, really is not very informative. It doesn't give us any useful information. If someone did a study and they said they found a covariance between X and Y, and they said that their covariance was 30, would that mean anything to me? Could I interpret that as being a high value or a low value? Well, not really. I wouldn't know what to make of it, and it wouldn't mean anything to me. And for that reason, if I did a research study and published a paper, I would not report a covariance in a paper that I published, because a covariance really wouldn't give a reader any useful information. So if a covariance by itself is not very meaningful, why then would we want to calculate a covariance? Well, a covariance has some very special important properties to it, and these are special important properties that make it possible to calculate a correlation, which is very meaningful. So, what are these special properties of a covariance? I'm going to go through and tell you about these important properties of a covariance, and as I'm doing this, see if you can guess, if you can think ahead and guess how we're going to use a covariance to calculate a correlation. So let's look at these fabulous, amazing, special, important properties of a covariance. First thing, a covariance will be as large as possible when you have a perfect positive correlation. So say, for example, we're doing that study where I'm looking at the size of rocks that were dropped on people's feet and the amount of pain that they felt after the rock was dropped on their feet. And say I have a data set and I have scores on X and scores on Y. I'll draw a bunch of X's down here at the bottom of the page to illustrate the fact we have a whole bunch of scores on X. So say each one of these X's is someone's score on the size of the rock that was dropped on a person's foot. And then everyone has a score on Y, which is the amount of pain they felt. And so I'll draw a whole bunch of Y's down here to indicate all these different scores on variable Y. So I've got scores on X and score on Y. And if I take this set of scores and arrange them so that I have a perfect positive correlation, if they're paired together so that we have a perfect positive correlation between X and Y, so that if we know someone's score on X, we know exactly what their score is on Y, and the highest, here's the person, maybe that person had the highest score on X, would be paired with having the highest score on Y, and so forth. So if these scores are all paired together so that we have a perfect positive correlation, then that's going to give us the highest possible covariance that we could get with this particular data set. And if these scores were paired together in any other way that doesn't produce a perfect positive correlation, that would make the covariance smaller. So given this data set, given this set of scores that I have on X and the scores that I have on Y, if I'm given this particular data set, this particular set of scores on X and Y, if the scores are paired together to produce a perfect positive correlation, then this set of scores will produce the highest possible covariance I can get. And if they're paired together in other ways, my covariance will become smaller. And essentially it'll go like this, that the stronger the relationship between X and Y, the higher the covariance. And as the strength of the relationship gets stronger and stronger, my covariance will become a larger and larger value. So the covariance becomes larger as the strength of the relationship between two variables gets larger, and the covariance becomes smaller as the strength of the relationship becomes weaker. And as you might guess, if I have a negative relationship, then the covariance will be as negative as possible when I have a perfect negative correlation between two variables. So the covariance gets larger and more positive as the strength of relationship gets stronger in a positive direction. If I have an inverse relationship, say I'm looking at the size of the rock that was dropped on people's feet and the amount of happiness they felt, in that case is one variable goes up, the other goes down. So that would be a negative relationship. And as the size of the negative relationship gets stronger and stronger, then my covariance will become more and more negative. So it will be the largest, most negative value it can be when I have a perfect negative correlation. It will be the most positive high value it can be when I have a perfect positive correlation. And as you might guess, it will equal 0 if I have no relationship. If the correlation between X and Y is 0, then my covariance will be 0. So covariance will be 0 when there's no relationship, and this value gets bigger and bigger as the strength of relationship gets larger and larger. So does this covariance have some kind of upper limit to it? I'm saying it gets bigger and bigger, but how big can it get? Well, it does have an upper limit. I'm going to say it this way. The covariance cannot be larger than your variance. Now, we actually have variance for variable x, and we have the variance for variable y. We were just looking at the formulas for variance and covariance. And we'll have one. So if I have two variables, I'll have one covariance between those two variables. And I'll have the variance of x and the variance of y. And the covariance cannot be larger than those variances. Or said a little differently, I'm going to say the covariance cannot be larger than a measure of averaged variance. In a little bit, I'm going to talk about a special way that we're going to take an average between those two variances. But for right now, we'll just say it this way. Your covariance cannot be larger than the averaged variance. So that's an upper limit. It can't be larger than that value. Or if you have a negative relationship, the covariance cannot be, the absolute value of your covariance cannot be larger than your averaged variance. And as you might guess along this line, it will actually equal your averaged variance if there's a perfect positive correlation. So if I have a perfect positive correlation between two variables and say the averaged variance was 30, well, if my correlation was, if my covariance was 30, then I'd know I'd have a perfect positive correlation. Because if my variance was 30 and my covariance was the same size, well, then I know that that covariance is the largest possible value it could be, and I know that it's the largest possible value it can be when I have a perfect positive correlation. If I had a variance, if my averaged variance was 30 and my covariance was only 15, well, then I know my covariance is half the size it could actually be. So my covariance is something that gets larger and larger as the strength of relationship between two variables gets larger, and that largest, biggest possible value it could be is a value that's equal to the average of my two variances. My covariance cannot be larger than my averaged variance, and that's the largest value it can be, and when I have a perfect positive correlation, it will equal my averaged variance. So here is an example to illustrate what I've been talking about. So say I was doing a study on blue-footed booby birds. The picture on your screen, I believe, is a picture of a blue-footed booby bird. And I believe some birds engage in a mating dance as a method to try to attract mates. And I think blue-footed booby birds might do this. So say, for example, I was doing a study where I went out and I observed some different blue-footed booby birds, and I looked at how long they engaged in a mating dance and how many mates they attracted. And let's look at this data set in the upper left-hand corner of the screen here. And in this data set, I've got 5 birds. So I did a study and I have 5 birds in my sample. I have Polly bird and Flaps bird and Tweety bird and Big bird and Fried bird. I don't know what kind of bird parents would name their bird Fried, but that's what I have in my example. And so Polly bird here, Polly danced for 8 minutes. So Polly's score on X is 8. And Polly unfortunately got 0 mates. So Polly's score on Y is 0. And down at the bottom, I have a scatter plot, and I've got where Y is 0 and X is 8. I put a dot right here. So that dot in the lower left-hand corner of my scatter plot is a score for Polly. And then Flaps danced for 10 minutes and got 2 mates. And so we can put Polly's score or Flaps score on the scatter plot down below here. So on X-axis, got a 10 down here on her X-axis and a 2 for Y. So I'll put a dot right there for Flaps. And Tweety danced for 11 minutes and got 3 mates. So I'll go down to our scatter plot, look at 11 minutes on X, and number of mates on our Y-axis was 3. So I put a dot right there, kind of in the middle of our scatter plot for Tweety. Big Bird danced for 12 minutes, got 4 mates. So I put the dot right here for Big Bird. And Fried Bird danced for 14 minutes on X and got 6 mates on Y. So I put that dot in the upper right-hand corner there. And so note on this data set, what we have here is a perfect positive correlation. Our dots line up perfectly in a straight line. And if we know someone's score on X, or if we know a bird's score on X, if we know how many minutes a bird danced, we could actually perfectly predict how many mates that bird got, because all of our points are just lining up just perfectly on that straight line there. So what we have here is a perfect positive correlation. So the data set on the left is illustrating a perfect positive correlation. Now the data set on the right-hand side note we have the exact same birds and the same numbers. So we've got Polly, Flaps, Tweety, Big, and Fried. And note that the minutes here, we've got 8, 10, 11, 12, and 14. Same minutes, 8, 10, 11, 12, 14. So that's exactly the same. The only thing is, for the Y variable, I've mixed up how many mates each bird got. So here, Polly bird got 0 mates, but over in my another example, it was Flaps that got 0 mates. Flaps got 2, but down here it's Fried that got 2. Tweety got 3 in our first sample, but Tweety got, actually it was the same there, that stayed the same. Big got 4, but then it was Polly got 4, and Fried got 6. So notice, we've got, it's the data set is the exact same numbers. So the numbers I have for variable X and the numbers I have for variable Y are the exact same numbers in these two data sets. The data set on the left and the data set on the right both include the exact same numbers. The difference is how I've paired those numbers together. The data set in the left, they're paired together to make a perfect positive correlation. This data set on the right, they're actually paired together to make a 0 correlation. There's absolutely no relationship between X and Y. In the data set on the right, the number of minutes that a bird danced is totally unrelated to the number of mates the bird got. And let's look at the scatter plot down below in the lower right-hand corner. Note that there's no line here. We've got our dots are all scattered around to kind of make a giant square here, kind of around the center point. If we had more dots and it was a 0 correlation, they just make a big cloud, a big circular crowd here. If I had a 0 correlation in lots and lots of cases, it would just make a big circular cloud of dots. So what we have here is a data set. On the left-hand and the right-hand side, we've got two versions of the exact same numbers. The difference is on the left-hand side, they're paired together to make a perfect positive correlation. On the right-hand side, they're paired together to make a 0 correlation. So let's consider what would happen if we were to calculate, say, a variance and, importantly, a covariance with these two data sets. So let's start with the data set on the left-hand side of the screen, the data set showing a perfect positive correlation. And let's look at variable X, the number of minutes that each bird danced. And let's calculate the variance for X. So we have scores of 8, 10, 11, 12, and 14. So we'll center those scores and then square them and then calculate the sum of squares, divide by degrees of freedom, and we will have the variance of X. And if we calculate that, the variance of X in this example is equal to 5. And so I'm going to put that right down here. I have SD squared. Recall that's our symbol for the variance, because a variance is a squared standard deviation. And a standard deviation is a square root of a variance. So SD squared is equal to 5 because the variance of X is equal to 5. And then if we calculate the variance for Y, we've got 0, 2, 3, 4, and 6. And if we center those scores and then square them, sum them up to get the sum of squares, divide by degrees of freedom, we would discover that the variance for Y, and I've made this come out all nice and neat, the variance of Y is also exactly equal to 5. So we've got an example here where the variance of X is 5 and the variance of Y is 5. So given this, you should be able to know what all these other question marks are. If we have a perfect positive correlation, and the variance of X is equal to 5, and the variance of Y is equal to 5, then just from that you should be able to know what is the covariance between X and Y. And in our example on the right-hand side of the screen, where we have a 0 correlation, but it's the exact same data set, what would the variance of X be? What is the variance of Y? And what is the covariance between X and Y? You should be able to tell me what all these values are. So, what are these values? And here are the answers. So recall that a covariance is a value that gets larger and larger as the strength of relationship between two variables gets stronger and stronger, to the point if you have a perfect positive correlation between two variables, then the covariance will be the largest value it could possibly be, and the largest value it could possibly be is equal to the averaged variance. So if I give you this example, if I say here we have an example where there's a perfect positive correlation between X and Y, which we have on our left-hand side of our screen, if we have a perfect positive correlation between X and Y, and if the variance of X is equal to 5, and if the variance of Y is equal to 5, then you know the covariance has to be 5, because if there's a perfect positive correlation, then your covariance will be equal to a measure of averaged variance. So if your variances are 5, then your covariance will be 5. Now let's consider the example on the right-hand side of the screen. Now note that variable x and variable y have the exact same numbers. So on the left-hand side of the screen, we have one set of numbers for x and y. And on the right-hand side of the screen, we have the exact same set of numbers. They're just mixed, the y variable is mixed up in a different order, but it's still the same set of numbers. So if the variance of x in our first example was 5, we know the variance in our second example has to be 5 because it's the same set of numbers. If the variance for y was equal to 5 in our first example, then we know the variance of y has to be 5 in our second example because although the numbers are rearranged, it's still the same set of numbers, so it would produce the same variance. And then the question, what is the covariance between x and y in our second example, or if we have a 0 correlation? Well, we just know if the correlation is 0, then our covariance is 0. That's all there is to it. So if we have a 0 correlation between x and y, then we know our covariance has to be 0. So those are we know that if we have a perfect positive association between x and y, our covariance will be the largest value it could possibly be, which is equal to a measure of averaged variance. So if your averaged variance is 5, your covariance is 5. But if you have a 0 relationship, then your covariance will simply be 0. And now we're ready for another song. This is the Variance and Covariance song. And the purpose of this song is simply to help you remember the formulas for a variance and a covariance. And in the song, the first 3 lines will be about how you calculate a variance, and the last 3 lines will be about how you calculate a covariance. So to calculate a variance, the first step is we need to calculate a sum of squares, where we take scores on x and we center those scores, and then we square them. That is, take your x and center it and times it by itself. And then we'll add those squares up to get a sum of squares. And then we're going to divide that sum of squares by our degrees of freedom, which is equal to our sample size minus 1. And that will calculate a variance. As the song says, now you've got a variance. That's what you have done. And in contrast, to calculate a covariance, we start off the same way. In both cases, we take an x variable, we center it. So with variance, we have our x variable, we center it. With a covariance, we take x and center it. But the difference is, with a variance, we times it by itself. It was centered x times itself. With a covariance, it's centered x times a partner, centered x times centered y. So for a covariance, we take our x and center it and times it by a partner. And then we're going to add up those cross products to get a sum of cross products. So with the variance, we got a sum of squares. Up here, we got a sum of squares. With a covariance, we get a sum of cross products. But in both cases, we divide it by our degrees of freedom, the sample minus 1. And so if we get our sum of cross products divided by degrees of freedom, that gives us a covariance. So as before, see if you can listen to the song, see how it goes, and see if you can sing along. This one's got a lot of words, but see if you could sing along with this one without looking at the words. And if you can, that would really help you get down clear what is the definition of a variance and what is the definition of a covariance. So here is the song, Variance and Covariance.
That's
And now we're ready to look at how we can use a covariance to calculate a correlation. And we've been talking about how a covariance is a value that will get larger and larger as the strength of relationship between two variables gets stronger and stronger, how it will equal 0 if there's a 0 relationship, and how your covariance will be equal to a measure of averaged variance if you have a perfect positive relationship. And by the way, these properties that I'm talking about, these are things that are true because we have used squared values in our formula for a variance. If you recall, when I was talking about the formula for a variance and a standard deviation, recall that I asked the question, why is it that we use squared deviation scores rather than absolute deviation scores in that formula? And I said the answer was because it gives the formula special properties so it can be plugged into other formulas and these other formulas will work. And this is one of those places where this is true. These properties that I'm talking about are true because we're looking at squared deviation scores. And if we had formulas that used absolute deviations rather than squared deviations, this would all fall apart. It wouldn't work. And our formula for a correlation wouldn't work. So how do we use a covariance to calculate a correlation? On the screen, I have a picture of two rocks. On the right-hand side of the screen is a large rock, and that rock is supposed to illustrate the size of the averaged variance for two variables. On the left-hand side of the screen is a rock illustrating the size of the covariance between two variables. And this rock on the left-hand side of the screen, we can ask the question, well, how big is that rock? We know that this rock is going to be somewhere between 0, just nothing there, and the biggest this rock could be, our covariance cannot be larger than the size of our averaged variance. So if you look at this rock on the right, how big is our averaged variance? Well, that's the biggest our covariance could possibly be. That's how big our covariance would be if we had a perfect positive correlation. So compared to how big the covariance possibly could be, how big is our covariance actually? Is it as big as it possibly could be? Is it maybe half the size it possibly could be? Maybe it's only a fourth the size it possibly could be. So what we want to do to get a measure of strength of relationship, to get a sense of how strong is the relationship between two variables, we can ask the question, how big is our covariance compared to the size of our averaged variance? How big is our covariance compared to the size, the biggest size that our covariance possibly could be, which is the size of our averaged variance? So how could we do that? Well, we can make that comparison by simply taking our covariance and dividing it by a measure of averaged variance. And that will essentially give us a value that tells us what is the percent of averaged variance that is covariance. That is, on a scale that ranges from 0% to 100%, where 100% is the biggest value the covariance could possibly be, that is 100% is a value equal to your averaged variance, on that scale, how big is the covariance? So we take our covariance divided by a measure of averaged variance to get essentially the percent of averaged variance that is covariance. And that is actually all a correlation is. So I have at the top of the screen correlation equals. A correlation is equal to a covariance divided by a measure of averaged variance, which will give us essentially what is a percent of the averaged variance that is covariance. And so putting everything together, I have at the top of the screen the formula for calculating a correlation. So we have Rxy, and the letter R is the letter we'll use as the symbol for a correlation. So if I have R subscript xy, that stands for the correlation between variable x and variable y. And I will use the letters COV to stand for the covariance. So we have the correlation between x and y is equal to the covariance between x and y divided by the standard deviation of x times the standard deviation of y. So in other words, our correlation is equal to a covariance divided by the product of our two standard deviations. Now, at this point, you might be thinking, wait a minute, that's not what I was expecting. Because on the previous slide, I just told you that a correlation was equal to a covariance divided by a measure of averaged variance. And the product of our two standard deviations does not initially look like what we might expect as an average of our two variances, but it actually is. The product of our two standard deviations actually is a measure of averaged variance. It's just not the usual way we calculate an average. It's a different way of calculating an average. So usually, the usual method we would use for calculating an average of two values is we add them together and divide by 2. For example, if I had two values, say the number 9 and the number 16, put 9 and 16, if I wanted to get the average of these two values, usually the normal method for calculating an average, I would simply add them together, 9 plus 16, and divide by 2, and that would actually, what would that be? That would be 12.5 was what I get. So this would be the usual method of calculating an average. But a different method, and I believe this method is called taking a geometric mean. It's a slightly different type of average, a slightly different type of mean. What I'm going to do here is I'm going to take my two values, I'm going to take the square root of each value, and then multiply those square roots together. So I could take the square root of 9, that would actually be 3, and then I'm going to multiply that by the square root of 16. If I was wanting to average, if I was wanting to get the geometric mean of 9 and 16, I'll take the square root of each and then multiply those two square roots together. So I'll take the square root of 9 times the square root of 16. That would give me 3 times 4, which would be equal to 12, which is a slightly different value. See, these are two slightly different methods. They don't give us the exact same value each way, but these are two different ways that we can calculate an average of something, and we're going to use this fancy geometric mean process for getting the average of our two variances. So if I take a variance and take the square root, say we take our variance of x, what do I get if I get, and I'll put a variance of x, so if I do SD squared, that's our variance of x, what is the square root of our variance? Well, if I take the square root of my variance, that gives me my standard deviation. So if I take the square root of my variance for x, that gives me the standard deviation of x. If I take the variance, if I take the square root of my variance for y, that gives me the standard deviation of y. So if I multiply my two standard deviations together, that is a way of getting the averaged variance of x and y. So the product of my two standard deviations is actually equal to a measure of averaged variance. So putting it together, we really do have a formula that's taking our covariance between x and y divided by a measure of averaged variance between x and y, and we're using this geometric mean approach where we're calculating our average variance by calculating the product of our two standard deviations. Now let's consider this question. What would the correlation be? That is, what would the correlation be the same as if, prior to analysis, we turned all the variables into z-scores? So for example, say we were doing that study where we had a sample of people that had accidentally dropped rocks on their feet. So everybody in that sample would have a score for rock size, the size of the rock that landed on each person's foot. And everyone in that sample would have a score for pain, the amount of pain that each person felt when the rock landed on their feet. So if we took all those scores on X, rock size, and we turned those into z-scores, and we took everyone's score on pain and we turned all those scores into z-scores, if we did that, our correlation would become the same thing as what? What would our correlation become the same thing as? Well, the answer is our correlation would become the same thing as the covariance. So why is that true? Well, if we turn a variable into a z-score, that will create a new scale that will always have a mean of 0 and a standard deviation of 1. So if x and y are both turned into z-scores, then both x and y will have a standard deviation of 1. And so if we look at our formula up here, if our correlation is equal to a covariance divided by the product of our two standard deviations, well, if both x and y are z-scores, then it will become the covariance divided by 1 times 1, because the standard deviation of x will be 1, standard deviation of y will be 1, so it becomes covariance divided by 1 times 1, and 1 times 1 is 1, and covariance divided by 1 is just your covariance. So if we, and I'll call this, if I standardize my variables, if I turn everything into z-scores prior to analysis, then my correlation becomes the same thing as my covariance. This is actually another way of understanding what a correlation is. I can say a correlation is actually a standardized covariance. The correlation is the covariance we would get if we standardize our variables prior to analysis. That is, if we turn all of our variables into z-scores prior to analysis so that every variable has a standard deviation of 1, if I standardize all my variables prior to analysis, then my correlation and my covariance are the same thing. So another way to define what a correlation is I can say a correlation is simply a standardized covariance. It's the covariance we get if everything's turned to z-scores prior to analysis. And it would be good to be able to depict what correlations of different sizes look like. And a good way to illustrate a correlation between two variables is to use a scatter plot. So here we have a scatter plot, and a scatter plot will have an x-axis, that's the bottom line running from right to left, that will give us scores on an x variable. And then we have a y-axis, that's the line going from top to bottom on the left-hand edge, that will give us scores on a y variable. And so every dot indicates where someone scored on the x variable, or where a case fell on an x variable, and where that case scored on the y variable. So this one I'm circling here looks like that's, well, right about at a 1 on the x variable, and what's that, maybe a negative 0.15 on the y variable. Now this picture that we're looking at here is depicting a correlation of 0. All these dots are scattered out all over the place, and they kind of form a great big circular shape, a great big circular scatter. And so the dots are really scattered out, and they form this circular shape, and this is depicting a correlation of 0. And here is a tool that's on the internet that can be used to depict correlation at different sizes. I can move the slider to the right, and it will depict a positive correlation. Here's a correlation of positive 0.44. Or if I move the slider back this other way, here's a correlation of negative 0.56. And so I can move this back and forth, and we can see what correlations of different sizes look like. Now, as I'm doing this, focus on the scatter plot on the left-hand side of the screen. This website also has these overlapping circles, and that's actually showing something called percent of variance explained, and that's something we'll be talking about later in this course. But for right now, just focus on the scatter plot and what it looks like if we have correlations of different sizes. So here's the correlation of 0, and then let's increase this correlation and see what happens to our scatter plot. Here's 0.09, here's 0.29, here's 0.39, so I'm going up in size, 0.53. So notice what's happening. As I'm going up in size, there's becoming less and less scatter. The dots are converging, and they're coming together to form this line that goes, now here's a perfect correlation of 1. Now at this point, we have a line that goes from the lower left to the upper right, and all the dots fall exactly on that line. So as the correlation gets stronger, we get more and more of that vertical line going from the lower left to the upper right. And as the correlation gets weaker, that line gets flatter and flatter, and the dots get more and more spread out. And so the dots are getting really spread out. Here's a correlation of just 0.12. And then once we get back to that correlation of 0, we have that circular shape, and our line now, that blue dotted line you see, just going flat across from left to right. And then if I start making my correlation negative, that slope starts going the other direction. From now it starts going from the upper left to the lower right for a negative correlation. And here's a correlation of -1. And once again, all the dots fall just perfectly on that dotted line. And in your notes, I have scatter plots illustrating correlations of different sizes. And on this page are examples of positive correlations. So on the upper left, we have a perfect positive correlation, a correlation of 1, where again, all the dots fall just exactly on this line that goes from upper left to lower right. And here's a correlation of 0.8 and 0.6. And we see as the correlation gets smaller and smaller, the spread of the dots gets further and further. The dots get more and more spread away from that line. And that line is also getting flatter and flatter. So when you have a correlation of 0, it's just a big circular shape, a big circular spread of dots. And this line is now going just perfectly flat, going from left to right. And then here are examples of negative correlations. So now we're starting off in the upper left with a perfect negative correlation, a correlation of -1. And again, all the dots fall on the line, but now the line is going from the upper left to the lower right. It's sloping down the other direction. And then again, as we get correlations that are smaller and smaller, the spread of the dots, that spread gets wider and wider. The dots get more and more spread away from that line till we have a correlation of 0 where they're really spread out. Our line is just going flat across, and that scatter forms kind of a big circular shape. And as we're looking at scatter plots depicting correlations of different sizes, we can consider that same question we considered with the D statistic about what types of effect sizes are typical or common or expected when you're doing research, when you're addressing important research questions about complex issues in psychology and neuroscience. What types of effect sizes are typical, and compared to what's typical, what might be a large effect or a medium effect or a small effect. And once again, Cohen has given us some suggested cutoff scores that we can use to identify small, medium, and large effects. Now, these cutoffs for a correlation are going to be different than the cutoffs we use for a D statistic, because a D statistic and a correlation are two different scales, two different ways of measuring effect size. So for a correlation, we'll say that a correlation of 0.5 or larger, we'll call that a large effect. A correlation of 0.3 or larger will be called medium. Correlation of 0.1 or larger will be called small. And less than 0.1, we'll call that trivial. And at the bottom of the page, I have some depictions of scatter plots showing you correlations of different sizes. Now, these sizes might be smaller than what I think most people envision when they think about research finding a correlation. My guess is that when most people hear about a research study finding a correlation between two variables, they might envision something more like a correlation of 0.8. Let me go back to that previous page. So here would be, here's a correlation of 0.8. And so my guess is, I'm not sure, but I would guess that when most people hear about a study finding a correlation between two variables, they might be envisioning a correlation of this size, somewhere around 0.8. But just like a D statistic of 2 would be a huge unrealistic D statistic, a correlation of 0.8 would be a huge unrealistic correlation. If you're addressing an important research topic about a complex issue in psychology or neuroscience, you're not going to get a correlation of 0.8. That's just an unrealistically large correlation. Again, the lesson to learn here is that when we're addressing important complex issues in research, we're not going to get huge effects like a correlation of 0.8. So in research on psychology and neuroscience, go back to my slide I started off with here, a correlation of 0.5, we'll call that this would be a large effect compared to what we typically get in research on psychology and neuroscience. Now, note that a correlation of 0.5 is still a large effect, and note that it might take you just a couple seconds, but if you look at it, you can tell there's a correlation here. One way to do this, if I try to draw a circle best I can, note that in the circle we have very few dots in the lower right and the upper left. There's not much here, but we do have some dots in the upper right and the lower left. And so as we look at that, we can tell we have somewhat of a linear effect there. So a correlation of 0.5 is one that it might take us a few seconds, but we can see it with the naked eye. Now a correlation of 0.3, that would be a medium effect. And here, if we look at it really hard, we might be able to tell, but it takes a little bit of effort. Now we have this dotted blue line here that kind of gives it away, but if that dotted blue line was not there, we'd have to work pretty hard to be able to tell there's a correlation. Now I can still do that. If I try to draw my circle here, I might do something like this, and I might still say, well, it seems like we still have fewer dots down in the upper left and lower right, but there's maybe more here. I didn't quite draw my circle right, but there'd be a little more in the upper right and lower left. And so if we look at it hard enough, it takes some effort, we can tell there's a correlation with a medium effect. Now with a correlation of 0.1, a small effect, if that dotted blue line wasn't there, I couldn't tell if that was a correlation of 0 or 1, or I couldn't tell what it was. I couldn't tell if we had a correlation of 0 or maybe a small effect. So a small effect is something that's so small we can't see it with the naked eye. So a large effect, correlation of 0.5, it might take a few seconds, but we can see that with the naked eye pretty easily. A medium effect is something that takes quite a bit of work, but we can still see it with the naked eye. And a small effect is something that we really can't even see it with our naked eye. And so that's what a correlation of large effect 0.5, medium effect 0.3, a small effect 0.1. And just as I did for D statistic effect sizes, I have here some results from different meta-analyses to give you examples of types of studies that produce different sizes of correlation. And this will further clarify what different sizes of correlation mean. And so these would be meta-analyses here that are producing correlation effect sizes. So these would be studies looking at the association between two numerically scaled variables and then averaging across those multiple studies that have been done to get what is the average correlation effect size across studies. And when I perused through the meta-analysis literature looking for a very large correlation effect size, the biggest one I could find is a meta-analysis reporting a correlation of 0.5, which again, that would be a very large correlation. And that's from a meta-analysis of 14 studies looking at the association, the correlation between something called self-compassion and psychopathology. So these would be studies where they had participants complete questionnaires. And one questionnaire measured something called self-compassion, and that's how much you feel compassionate towards yourself. It's kind of like you can be compassionate towards other people, but are you compassionate towards yourself? If you make a mistake, do you go easy on yourself and don't blame yourself and don't feel too bad about it? And they measured, people filled out a questionnaire, and they answered questions that measured the extent to which they had self-compassion. And then they completed another questionnaire that measured the extent to which they had psychopathology. It could be feelings of depression or anxiety or other types of psychopathology symptoms. And then actually what they did in this study is they reverse scored psychopathology so that a high score means you have less psychopathology, you're more healthy, and a low score means you have high psychopathology. So it's actually anti-psychopathology. They reverse scored it. And this is actually an important lesson to keep in mind. When we're dealing with correlations, we always have to pay attention to whether or not the correlation's positive or negative. Is it a negative association between two variables or a positive association? But also, we can keep in mind the fact that if I reverse score a variable, for example, if I take a scale measuring psychopathology, so that a high score means you have more psychopathology, and then I just reverse score it, I flip the scoring around so that a high score now means you have low psychopathology, and a low score means you have high psychopathology. So I take my psychopathology scale and I turn it into an anti-psychopathology scale. If I reverse score it, then I'll flip the direction of my correlation. So because they have self-compassion and psychopathology is reverse scored, so it's actually measuring anti-psychopathology, it still is a positive correlation here. So our correlation is 0.5. It's a very large effect. So I have over here, say large effect, and here's what that correlation is, that same scatter plot of what a correlation of 0.5 is. Now, if you recall when I gave you examples from different sizes of D statistic, our largest effect I could find there was a D statistic of 1, and that was for a treatment of post-traumatic stress disorder, and all the studies in that example came out of the same lab, and that made me a little bit suspicious of that result. That when you get results that are really big, sometimes those results can be a little bit questionable. And we have the same thing here. It's not so much the results are questionable, maybe it's just that they're not that impressive because we have a correlation between two scales measuring very similar constructs. These are two self-report scales. So people report, they fill out a questionnaire reporting how much they feel compassionate towards themselves, and then they fill out another questionnaire measuring how much they have psychopathology symptoms. And these are kind of two similar types of questions. I feel anxious, I feel depressed, I blame myself. So if I say I blame myself, that would be a self-compassion item. If I say I feel depressed, that would be psychopathology. So these are two very similar types of questions on a self-report questionnaire. And so it's not that surprising that we would get a fairly high correlation between these two variables. So an example of a very large effect, a correlation of 0.5, is a meta-analysis. They had 14 studies that found a strong correlation of 0.5 between self-reported on a questionnaire, self-reported self-compassion and self-reported psychopathology, or actually it was anti-psychopathology because they reverse scored it, and a correlation of 0.5. And now, how about a correlation of 0.4? So a correlation of 0.4, we're now dropping down to a medium effect size. So what type of study would produce a correlation of 0.4? And the example I have here is studies regarding the association between marital quality, the quality of one's marriage, and overall life well-being. So these would be studies where they had people who were married, and they gave them questionnaires where they asked them to rate the quality of their marriage, how happy and satisfied they were in their intimate relationships. So people completed a questionnaire measuring their marital quality, and then they completed another questionnaire measuring their overall life well-being. This is actually similar to the psychopathology or the anti-psychopathology variable we looked at on the previous example. So an absence of psychopathology would be high well-being. And well-being could also include feeling happy and satisfied with one's life. So studies where they looked at self-report measures of marital quality and self-report measures of overall life well-being found a correlation of 0.4, and we had quite a few studies in this meta-analysis. There were 137 studies in this meta-analysis. Now, one thing to keep in mind, both this example and the previous one, these examples are the two largest correlation examples that I'm showing you, and both of these examples involve situations where researchers are looking at correlations between two self-report scales. And in general, if you're doing research looking at correlations between self-report scales, it's easier to get larger correlations in that type of research than in other types of research. So our example of a medium effect, correlation 0.4 specifically, is the correlation between marital quality and overall life being based on results from a meta-analysis with 137 studies. Now, what about a correlation of 0.3? So a correlation of 0.3 would still be in the range that we would call a medium effect. So what type of study would produce a correlation of 0.3? And the example I have here are studies investigating the correlation between therapeutic alliance and psychotherapy outcome. So these would be psychotherapy process studies where researchers are looking at processes occurring during psychotherapy and how much those processes correlate with outcomes at the end of psychotherapy. So these would be studies where at some point near the beginning of psychotherapy, maybe within the first couple weeks, clients were asked to complete a measure of therapeutic alliance. They were asked to complete a questionnaire assessing the extent to which they felt they had a strong alliance with their psychotherapist. And then after therapy was all done, at the end of therapy, they were measured on an outcome variable that was assessing whatever they were being treated for. So if they're being treated for depression, it would be a measure of depression. If they're being treated for anxiety, it would be a measure of anxiety. And then we have a meta-analysis that looked at quite a few studies. We have 201 studies, so quite a few studies investigating correlations between therapeutic alliance and psychotherapy outcome. And across all these studies, the average effect size, the average correlation was 0.3, which would be a medium effect. And one thing to note here is that this is a very important effect, but it's also in the medium range, which is the range that if we look at the scatter plot, we have to look kind of hard to be able to detect it. A medium effect is that effect that we can see it with the naked eye, but we have to look kind of hard to be able to see it. And this is true. We have a very important type of finding here about the relationship between therapeutic alliance and psychotherapy outcome. That's a very important finding, but it's not going to be a finding that we look at the scatter plot and see right immediately, oh my goodness, that's a huge effect. It's going to be a medium effect, and it's an effect that we have to look at kind of hard to be able to see it with the naked eye. So correlation between psychotherapy alliance, psychotherapy outcome, correlation of 0.3, a medium effect. What about a correlation of 0.2? So with a correlation of 0.2, we'd be dropping down into a small effect size. So what type of study might produce a correlation of 0.2? And the example I have here are studies investigating the correlation between parenting and child delinquency. So these are studies that would look at different types of positive parenting. For example, to what extent do parents use what might be called supportive parenting, where they encourage and support their children? And to what extent do parents use parental monitoring? Are they aware of where their kids are? Are they keeping track of what their kids are doing? So those would be some examples of positive types of parenting. And then we could look at how parenting correlates with child delinquency. That would be, are the children getting in trouble? Are they getting involved in drug use? Are they getting in fights? Do they get in trouble at school, or do they get arrested? and a meta-analysis looking at 161 studies. So again, we have lots of studies here investigating the correlation between different types of positive parenting and child delinquency, and our correlation is 0.2. Now, it might surprise some people that that correlation is relatively small. Some people might have guessed that parenting would produce a bigger correlation in predicting child outcomes. This is a small effect. If I didn't have this dotted blue line here, if I just looked at that scatter plot, it might be difficult to look at that scatter plot and even detect there's a correlation at all, because a small effect is one that's really too small to detect with the naked eye. So why is our effect size here so small? Well, it's so small because we're trying to look at a very important question. Child delinquency is something that's very complex. So if we think about it, it's really not that surprising that we have a small effect, because we're trying to predict something very complex. And no matter what we look at, we're probably going to find a small effect. It's not that parenting is unimportant. It's not that parenting isn't an important variable in correlating with child delinquency. It's just that there's probably many variables, and parenting is one of them, and we're not going to find any one variable that produces a huge effect if we're trying to understand something as important and complex as child delinquency. So in some ways, as the complexity and the importance of the variables are that we're studying, the effect sizes tend to get smaller and smaller. So an example of a small effect, correlation of 0.2, is a correlation between parenting and child delinquency. And finally, what about a correlation of 0.1? So a correlation of 0.1 would be a small effect. In fact, it would be a very small effect, right on the borderline between small and trivial. So what type of study would produce a correlation of 0.1? And the example I have here is actually one of my favorite examples, because we get a correlation of 0.1 in the correlation between clinician confidence and clinician accuracy. So this comes from a meta-analysis looking at 36 different studies, and these were all studies investigating clinicians of one type or another. It included both psychologists and medical doctors, and in these studies, these clinicians first gave some kind of diagnostic judgment, and then importantly, after they gave their diagnosis, they were asked, how confident do you feel that you've made the correct diagnosis? So the key variable here is clinician confidence. So after a clinician, a psychologist or a medical doctor, after a clinician has given some kind of diagnostic judgment, how confident does a clinician feel that he or she has made the correct diagnosis? And in these studies, they looked at clinician confidence, and then these were all studies where the clinician's diagnosis could be verified at a later point in time. So for example, in some cases there were medical doctors giving a diagnosis that could be verified by an autopsy at a later point in time. Or sometimes a clinician was making a judgment about whether someone might be institutionalized in the future, and that could be verified by legal or psychiatric records. Or sometimes clinicians were making a judgment about the extent to which the client was likely to improve, and that could be measured at a later point in time using objective tests. So these are all studies, 36 studies, where they had investigating clinicians, and clinicians were making some kind of diagnostic judgment, and then after making this judgment, they were asked to rate the confidence of their judgment. And the question here is, if someone feels confident that they made the correct judgment, does that confident mean they're more likely to have given an accurate judgment? Do people feel more confident when they're more accurate, and do they feel less confident when they're less accurate? Or is your confidence, when a clinician feels confident that he or she has made the correct judgment, is that confidence unrelated to the accuracy of the judgment? And we find here that, well, it is related, just a very, very, very tiny itsy-bitsy amount, not very much. The correlation is a very small effect. The correlation of 0.1, the correlation between clinician confidence and clinician accuracy. That is, how confident do clinicians feel that they've made the right diagnosis and how accurate they really are. That correlation is a small effect of 0.1. And that's everything for Part B of Unit 2.